All right, so we've already talked about density, and we've talked about how to measure density by calculating mass and volume. Now, how would we calculate density or volume if my cube or my object wasn't perfectly shaped and I couldn't just measure it with a ruler? Well, that's what we would refer to as an irregular shaped solid. An irregular shaped solid is something that's not perfectly rectangular, like a rock or maybe a key. Okay, so how would we measure the volume of objects such as that? Okay, that's what we're going to talk about today. So an easiest way to measure the shape or the volume or density of these objects is by using water displacement. And we already used the example. If you were to fill your bathtub up all the way to its highest point without the water spilling over, as soon as you step into that bathtub, the water spills over. Okay, water is being displaced. We can do the same thing to measure the volume of objects that aren't perfectly rectangular or square. Okay, so the easiest way to do this is to find the volume of that irregular shaped object is to take your final liquid volume and subtract your initial liquid volume. So for example, over here on the left, I've got a cylinder that's got 10 milliliters of water in it. If I drop a key into this water, I should notice that the water level rises. And now it's at 14 milliliters. So my initial volume was 10 milliliters. My final volume is 14 milliliters. So my final volume minus my initial volume gives me 4 milliliters. So that key has a volume of 4 milliliters. So now I can calculate the density of that key if I know the mass is 11.5 grams. So I remember density is mass divided by volume. If the mass of this key is given to me, it's 11.5 grams, and the volume we calculated or measured was 4 milliliters, then 11.5 divided by 4 is 2.87 grams per milliliter. So the density of that key is 2.87 grams per milliliter. I did that without even measuring anything with a ruler because it's an odd shape. I can't measure all the little teeth here, and this thing is round and cylinder, and then this little thing notch that sticks out, and this circle part that's the handle. It's difficult to measure all that with a ruler. So when we have shapes like that that are difficult to measure with a ruler, we're going to use volume, water displacement to measure that volume and ultimately find the density of that object. So the next example here, we want to measure the density of a hammer, a toy hammer. So here's my hammer, and again, it's irregularly shaped. I can't exactly take a ruler and measure this part because it curves, and then this part is thicker than the other, and it's got a handle that's also thicker than this part. You can't exactly measure that with a ruler. So what we could do to measure the volume is to pour it or dump it into a bucket of water or a cylinder of water. Well, if I'm looking at my water and I'm looking at eye level, remember I want to look at the bottom of the curve. The bottom of the curve is roughly right there. And it looks to be 65 milliliters. So my final volume is 65 milliliters. I'm sorry, my initial volume is 65. So let's write that right here, 65 milliliters. What was my final volume? Well, when I put the hammer inside the water raises all the way up here. So again, at eye level, I'm looking at that meniscus, the bottom curve of the water, and it looks to be, here's 60, here's 65, here's 66, 67, 68, 69. It looks like it's all the way up to 69. It's not quite at 70. It looks like the final volume is 69 milliliters. So 69 minus 65 gives me 4 milliliters. So this toy hammer has a volume of 4 milliliters. So now I can find the density. And up here above it told me the mass was 9.5 grams. So density is mass divided by volume. The mass we said is given to me, it's 9.5. Divided by the volume we decided was 4. And when I divide those two together, I get 2.37 grams per milliliter. Okay, and the last part on this practice problem number 3, I want to calculate the density of a 3.85 gram cube if it measures 1.5 centimeters on a side. Well, if it's a cube, then I know that all the sides are that same. They're all 1.5. So I know that this side is 1.5. I know this is 1.5, and I know this is 1.5. So if I want to measure the volume of this cube, I know I can measure length times width times height. So if the length is 1.5 times the width is 1.5 times the height, which is 1.5, 1.5 times 1.5 times 1.5 gives me 3.375 cubic centimeters. Okay, so now I want to know the density of this block, and it tells me the block has a mass of 3.85. Well, density equals mass divided by volume. The mass is given to me, 3.85, divided by the volume we just determined to be 3.375. When I divide those two, I get a density of 1.14 grams per cubic centimeter. And lastly, what would happen if this cube were dropped into a glass of honey, oil, or water? So remember, water has a density of 1 gram per milliliter. And it shows me honey has 1.36 grams per milliliter. Cooking oil is 0.92. So 1.36 is greater than 1. 0.92 is less than 1. So honey, if I put this density, this block that has a density of 1.149, is 1.149 enough to cause it to sink, float in the honey, oil, or water? Well, 1.14 is greater than or less than 1.36. 1.14 is less than 1.36. So in honey, it's going to float. 1.14 is less than or greater than 0.92. Well, I know that it's greater than 0.92. So the block has a density of 1.14 grams compared to the oil that is greater than 0.92, so it's going to sink. And 1.14 is also greater than 1 for water, so it is also going to sink in water. Okay, on the back. Now we need to figure out how to calculate percent error. So when we do an experiment or a lab, it's sometimes difficult to achieve perfect results. So we're human, we make mistakes, maybe we round when we shouldn't round. There's human error typically. So a lot of times there is some error. You need to be able to know how to calculate the percent error, or how far or how off our results are, and that is what percent error is. It's how far or how close you are to your actual results. Okay? So percent error compares our results to the actual value. So what the results should actually look like. Okay? We also call these the accepted value. We could call them the true value. Or we can call them the accurate value. That's what we want to achieve. That's what it should look like. Our results should be is an accepted value, a true value, or an accurate value. Now, the value that you actually calculate in your lab, again, you're human. You might make mistakes. You are rounding. You didn't look at the bottom of the meniscus when you should have, whatever. All of these values are called experimental values. Okay, these are the values that you actually get in the lab, okay, based off of your data and calculations. So, is it best to get a high percent error or a low percent error? Well, the idea is to get the percent error as close to 0 as possible. So the closer to 0, the better. Okay, so 0 means that you didn't make any mistakes at all. So the closer you are to 0, the more accurate your answer is going to be. Okay, so what we see down here is our percent error equation. This is very important. Make sure that you know where to come back and look for this. This is also on your formula chart with the periodic table. All right, let's look at an example here. It says the accepted density of calcium is 1.54 grams per milliliter. A student's lab measurement resulted in a density of 1.25 grams per milliliter. Calculate the student's percent error. Well, the accepted density, this is the actual density. It's telling you what the actual density is. So I'm going to label that with an A for actual. The measurement, what the student measured in the lab, came out to 1.25. That is what they measured in the lab. That's the experimental value. I want to calculate percent error. So percent error, I'm going to write percent error equals, and it's the absolute value. So if you ever calculate a negative, then the absolute value automatically makes it positive. So the actual value we said was 1.54 minus the experimental value, what they got in the lab, was 1.25 divided by the actual value again, which is 1.54. Okay, remember it's the absolute value. So whatever I get in here, when I divide these two, subtract and divide, I ultimately need to multiply by 100. And when I do that, I should calculate 18.83%. Now, 18.83 isn't very close to 0. So 18.83, in my opinion, is pretty high. Okay, a lot of times if that was the case, I might make you redo your lab or maybe try to find the errors myself so that I can help you, because 18.83 is a little high. You want it a lot closer to 0. Ideally, less than 10% is a lot better. So here's another example. It says Brianna and Mark measure the volume of water as 25.5 milliliters. The mass they measure is 26.17 grams. What will they calculate as the density of water when they use these numbers? So let's calculate density. Okay, first it gives us the volume, it gives us V, and then it gives us M, 26.7. I need to calculate D, density. So density equals mass divided by volume. So the mass is 26.17 divided by the volume, 25.5. When I divide those two together, I get 1.07. I'm sorry. It should be 1.02 grams per milliliter. So the actual density, what we've discussed already in the notes, is 1.0 grams per milliliter. So I want to calculate the percent error. So the actual is 1.0 grams per milliliter. The experimental, what they calculated in the lab, is 1.02. So let's plug that into our calculation. So percent error equals, and it's going to be the actual value, which is 1.0, minus the experimental value, what they calculated in the lab, which is 1.02, divided by the actual again, which is 1.0. Okay, so subtract these two, divide by 1, and your last step is to multiply by 100. When I do that, I get a percent error of 2%, which is a lot closer to 0, so this measurement, this calculation, is a lot more accurate. So what makes something accurate? What makes something precise? Okay, there is a difference. So accurate means the correct or true value. Okay, accurate means the value that you should calculate. Okay, precise means that your values are all close to each other. So all your values are very close to each other, even though they may not be accurate. They might not be right, they may not be wrong, but they're all very close to each other. Okay? So if you look at the example up here with a bullseye, if you've ever played darts, most often you want to hit a bullseye. Okay? So if you can hit the bullseye every single time, you are said to be very accurate, because that's what you really want. That's the idea behind it, the goal. But if you don't hit the bullseye, but all your darts hit the same number or in the same section, the same spot, you didn't hit your target, but all of your darts hit in the same place. So that is what we call precise or precision. All your data is very close to each other. However, it is not the actual data. So our first example says, when playing darts, the goal of the game is to hit the center bullseye, just like we mentioned. Evaluate the targets below and determine if they have low or high accuracy and low or high precision. So let's look. Here's A. A looks like they didn't hit the bullseye. They're kind of all scattered together. They're not very close. So not any of them hit the bullseye. So I would say low accuracy. So I'm going to abbreviate, low accuracy. Now, they aren't very close, they're very spread out. So I would say they have low precision also. And I'm going to abbreviate that as well. Low precision. If I look at B, none of them hit the bullseye. Okay, so they have low accuracy. But they are all very close together in a group. This would be a high precision throw. And when I look over here at the next one, again, not a single one hit the bullseye. So low accuracy. And I've got one here, 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 here. They're not very close together. That's low precision. And the last one here, D. Now I've got all four of them in the bullseye. All four of them are very close together. So these would have high accuracy and high precision. All right, let's look down here at example 2. It says the density of aluminum is 2.72. Students measured the density of 3 different samples of aluminum and recorded their results in the data table below. Evaluate the results of each group. Well, it says Group 1 had a sample of 2.72, 2.75, 2.73. These would be all very close to each other. So I would say they are accurate and precise. So it would be both. Group 2 has 2.32, 2.07, and 1.65. Not any of these are really close to 2.72. So I would say they're not accurate. So accuracy would get an X because they're not accurate. Precision, they're not very close together, so precision is going to get an X also. They are neither. Okay, and the last one, you got 2.8, 2.8, 2.87. Well, they're not very close to 2.72, so as far as accuracy goes, they're not accurate, but they are all very close to each other, so precision gets a check. And the last one here, a student measures the density of 3 samples of water. She gets 1.45, 1.43, and 1.45. Well, we know the density of water is 1 gram per milliliter. So if I look, not any of these are close to 1 gram per milliliter. So they are not very accurate. However, these are all 3 very close to each other. So, yes, it is precise. Values are very similar. So if your values are similar, then you are precise. If your values are very close or on the expected value, then they are said to be accurate.